Séminaire euh, l'histoire de l'univers. Donc, Yann a fait un master par ici, puis enfin, une thèse en Montpellier. Il s'est déplacé après un temps en Espagne, en Allemagne pour des postdocs, et puis maintenant il est directeur de recherche à l'IJCLAB. Et donc, en plus de son activité de recherche, du coup, il fait un grand effort pour vulgariser et populariser la science auprès d'un grand public. Et donc voilà, là, il va s'adresser à un physicien du solide.
Bonjour et merci pour l'invitation. Effectivement, quand Emmanuel m'a proposé de donner un colloque ici, j'ai accepté avec enfin, un grand plaisir. Et donc un colloque, c'est jamais facile de donner un colloque parce que c'est pas du grand public, c'est pas non plus une conférence de spécialistes, donc il faut trouver un bon équilibre entre les deux. J'espère avoir trouvé un équilibre sans être trop naïf dans mes explications, sans être trop technique dans mes résultats. L'idée étant de vous donner un peu une idée de l'histoire, de l'évolution de l'univers, depuis le Big Bang jusqu'à nos jours et au-delà, parce qu'on ira un peu plus loin que 13,8 milliards d'années. Beaucoup des résultats que vous verrez datent d'il y a moins de 10, 15 ans, 25 ans maximum, je dirais, pour la découverte de l'énergie noire. Donc, ce sont des découvertes quand même relativement récentes, hein, on va dire 98-2000 pour la plus ancienne, parce que la compréhension de notre univers, en fait, a beaucoup évolué depuis les 20 dernières années, principalement dû, comme j'en ai parlé à midi avec une de vos collègues, à la précision obtenue dans les différentes expériences. Et j'insisterai aussi donc sur le bestiaire, ces animaux qui apparaissent dans cette histoire de l'univers qu'on n'a pas actuellement sur Terre, donc des inflatons, de la matière noire, enfin on les a, mais on ne les a pas encore découverts, je dirais, ça reste des animaux un peu théoriques. Donc j'ai illustré ici l'inflaton par un champ phi qui oscille. Alors l'inflaton, on le décrit toujours par phi, hein, quand vous voyez une lettre phi, c'est l'inflaton, la particule responsable de l'inflation qui est sans doute de même nature que celle responsable de l'accélération de l'univers. Donc, c'est un champ homogène qui oscille, je reviendrai dessus. C'est un condensat, en fait, comme un condensat de Bose-Einstein, qui est homogène sur tout l'univers, parce que l'expansion de l'univers est très homogène. Donc, ça veut dire qu'il nous faut un champ qui est lui aussi très homogène, mais pas totalement homogène non plus, parce que vous aurez remarqué qu'il y a des galaxies et des étoiles et des planètes. Donc, le champ doit être homogène, mais pas trop à 10-5 près, on va dire, ce que donnent les données du fond diffus cosmologique. J'ai aussi illustré ici des trous noirs aussi, parce que je parlerai des trous noirs primordiaux, les trous noirs qui ont été formés au tout début de l'univers. Pareil, toujours des hypothèses et pas observées, mais des grands domaines de recherche. Alors, un peu de publicité, comme il vient de sortir aujourd'hui, le livre, là, il y a l'exemplaire tout chaud que je viens de recevoir ce matin, donc, de la seconde édition de Particularly Dark Universe. Donc, si vous voulez aller plus loin dans les calculs ou dans les détails de ce que je vais expliquer dans le livre, en général, c'est quand même bien détaillé. J'ai un effort de pédagogie sur. C'est un livre niveau, voilà, niveau doctorant ou post-doctorant. Hop, voilà, je ne sais pas ce qu'on fait, mais. Ah, d'accord. Je continue. Donc, et une deuxième publicité pour un deuxième livre qui est d'un niveau voilà, plus vulgarisé, mais tout ce que je vais parler sera aussi dans le livre Nouvelle Physique. Bon, on a été récompensé du prix Bourrienne cette année, où j'explique aussi toutes ces découvertes de ce qu'on appelle la nouvelle physique, énergie noire, matière noire, trou noir, Big Bang et physique des particules, principalement neutrinos et supersymétrie. Maintenant, pour ceux qui veulent aller encore un peu plus loin, il y a les articles. Alors là, bon, si vous voulez, on laissera le PDF, j'imagine. Vous avez une somme d'articles pour ceux qui veulent voir plus en détail les calculs. Si certains points vous titillent, vous verrez que ils sont assez bien détaillés dans les articles qu'on a. Ça, c'est les articles qu'on a fait avec notre équipe. Alors, je mets souvent la photo d'équipe hein, qui est formée de post-doc et d'étudiants, Mathieu, Riajoul, Mathias, Young, Esojolo et Simon. Voilà, beaucoup des résultats que vous verrez, surtout numériques, ont été produits grâce à ces personnes qui sont soit étudiants ou post-doc en général. Donc voilà l'histoire de l'univers classique. Hein. On part d'un Big Bang il y a 13,8 milliards d'années, une phase d'inflation très rapide, hein, exponentielle, et puis on a un univers de radiation, on a un fond diffus cosmologique, et on a pendant 13,8 milliards d'années l'évolution de l'univers. C'est un peu cette histoire que je vais essayer de vous raconter. Et je vais aller un peu plus loin, parce que comme on utilise des simulations numériques, je vais le faire tourner jusqu'à 10 puissance 102 années. Donc on va aller quand même assez loin, jusqu'à l'évaporation de notre trou noir central Sagittarius. Voir un peu comme on a les simulations qui marchent, on se dit pourquoi s'arrêter à 13,8 milliards d'années, autant aller plus loin pour voir quel est l'avenir. de notre univers, qui est dominé, hein, vous l'avez vu, là, il y a une petite phase d'accélération. Hein, il y a 8 milliards d'années, l'univers est reparti en phase d'accélération, il s'est stabilisé. Et il y a 8 milliards d'années, l'univers est reparti en phase d'accélération, donc d'expansion accélérée. Hein, il a toujours été en expansion, mais en expansion accélérée. Donc, le colloque sera donc un mélange de découvertes récentes. Oh, in English, sorry, I was in French. In English, who doesn't speak French? Okay, in English, English, French, is as you wish. En français, vous me dites, hein, vraiment, ok. It's okay? Bon, on va sur le français alors. Les transparents sont en anglais. C'est vrai que je suis parti sur le français naturellement. Donc des découvertes récentes. Oh, parfois, peut-être je switcherai en anglais en fait instinctivement. Donc des, I will do in English maybe for those in okay. Recent discoveries, frequently asked questions, and some historical perspectives. So it will be a mix between all these stuff that you can you can see. So what is a roadmap? I will show you. So my roadmap will be very simple. I will begin at 10 to minus 38 seconds after the Big Bang, where we are now, up to now, and 10 to 102 years. That roadmap is a long way for 1 hour. And the color I put here correspond to which was the field who dominated the universe. So in green, it is when you have a field which is a cosmological constant or inflaton, a field with negative pressure in green, radiation in yellow, and matter in purple. Okay, so this is universe dominated first by the inflation, so by a field with a negative pressure, with a matter, with a radiation field, you can call it light if you want, matter fields, and then inflationary phase since 8 billion years. After, we don't know. So I divided into primordial universe, present universe, and future universe. Okay, that will be very easy. So if we begin first, so I will not say nothing, of course, before 10 to minus 38 seconds, because I don't know, and not, of course, before 10 to minus 43 seconds, because this is a Planck scale. So I have not a quantum theory of gravity, so I cannot tell anything before 10 to minus 43 seconds, because it's above the Planck mass scale, or below the Planck length scale. So I have no theory describing it. So what I could say, okay, a priest can say the same, or a philosopher can say the same. I have no reason to tell anything before that because I don't have any clue of what's happening. I don't have a theory to tell what's happening. So the white region is a region which is still valid in our field, but we don't have hints of what can we see because we don't have any experimental data between 10 to minus 43 to 10 to minus 38. So it seems for you small numbers, of course, because I put seconds. For a particle which is living 10 to minus 40 seconds, this is a long way. So people say, oh, it's very small, 10 to minus 38 seconds. It's because I put second, right? I put any kind of units, can be a long way. So I will begin from the Big Bang. Let's say for the beginning of what we can describe as a space-time to now, we call it the horizon size, if you want, which is the smallest horizon size we can see. So if I put some numbers to give you some numbers, so in 10 to minus 36 seconds, from 10 to minus 38 to 10 to minus 36 seconds. So in 10 to minus 36 seconds, the universe grows from 10 to minus 29 centimeter to 1 centimeter. So this is the size of the universe at scale here. This is the size of the universe after the inflation. So everything is inside there. We are here. The sun is there. Platon and Leonardo da Vinci is there. So this little square represents the universe after the phase of inflation. So it's quite small. So our horizon, this is our universe. I will explain what I mean. When I tell universe, I mean visible universe, the universe where we live now. The size of universe. Universe is, of course, much larger than what we see. But this is the universe we see now. It is the size of the universe we see now after 10 to minus 36 seconds. So, of course, it's very violent. The phase is a violent phase. And sometimes there is confusion of the term Big Bang, because when you talk about Big Bang, people think as an explosion. It's normal because the name Big Bang feels like an explosion. So people imagine a Big Bang, something like that, right? This is when we say Big Bang, people imagine an explosion and everything going out, and you see everything going further and further away. And of course, usually the question I have is, where was the Big Bang? And this question has a signification if you have one point of view and no signification with a modern point of view. So of course, if you have an exclusion to that approach, you have an explosion and you have some galaxies going further than the other one, okay, and you have a center of something, and if a bomb explodes, you should observe the same thing, okay? But this is not what we observe. We observe something like this, which is all the galaxy from all the directions go forward from us, okay? Escape from us with the same velocity. So one explanation is that we are the center of the world. The Big Bang took place on Earth 13.8 billion years ago. It's true. You can make a theory with that. And taking an explosion here and all going away, you will see the galaxy which is twice further from us receding twice faster than us. It's normal. If they are twice faster, they recede. They are twice further than us. Completely logical, like a bomb exploding. Exactly the same. But of course, after Copernicus is not what we think. So the other point of view, it is that everybody is the center of universe. Okay, which means that you have to suppose the universe. I put a grid in my universe. Okay, this is a grid in the universe. And the light is extracted from the Big Bang here, okay, at the time. And when the universe expands, you receive the light nowadays of the point there, which is at 13.8 billion light years from us, a little bit more, 42 to be precise, because universe has extended from here to here. So 13.8 billion light years were there, and now it's 40 billion light years. But the light we see now is the one which has emitted from the point here 30.8 billion years ago. And this point now is at 42 billion light years away from us, okay? So this is what's happening. But this is what we call the CMB, okay? I will discuss it about. But if I have surely another part of space, someone else is going the same talk that I'm giving now, I can imagine, and they are observing the same light which has been emitted at the same point. They observe exactly the same CMB. This is a cosmological principle, if you want. Whoever is in the world nowadays, now, at the present time, whoever is in the world, in the universe, in the multiverse, observe exactly the same CMB, cosmological microwave backgrounds, right? That's the main point of Einstein cosmological principle, okay, which means that wherever you are, whenever you are, everybody sees the same physics, okay? And in this case, you can observe that everybody believes is the center of the world. Of course, I will discuss about only this square here, which is the one we see, because the light which has been emitted here on this part of universe is on its way, and we will see it tomorrow, the day after tomorrow, in 1 million years, in 1 billion years. So now we observe nowadays, at present time, we observe the light emitted here, but of course the light is already passed on the Earth. So nowadays we observe the light was emitted here, now the light emitted here. So every time, every second, we see another part of universe. Okay, so I will discuss about only this part, this square of the universe. This is the one we see. So who is responsible of this stretching of the field? I'll just show you. I'll show you a stretching square, stretching chess playground. So the modern interpretation of this, it is the field responsible for this stretching is what we call the inflaton fields. So the inflaton field is a classical field. It's not quantum field. It's a classical field, okay, like a Maxwell classical equations, okay? It's not quantum, which is homogeneous because you should extend the universe, expand the universe the same way on the north, on the south, on the west, on the east, because we see a completely homogeneous universe. So this expansion is almost homogeneous. That's why I say quasi, because of course you have some little inhomogeneities, which we call Earth, Sun, and galaxies. And the field is oscillating, in fact, and you follow an equation of motion very easy. So this is the equation of motion of the fields. Very easy to recognize. H is a Hubble constant. H is A dot over A being the scale factor. So it's an easy equation of motion. We depend only on time. You see, there is no position, only time, t. It's homogeneous, no position. There is a little, I will say, inhomogeneities, but I will discuss them after. And you can show that it's equivalent to an equation of states here with a field which has a density of energy rho phi, okay? So it's very equivalent. So these two equations is equivalent. If you define a density of energy, which is kinetic energy plus potential energy, 1/2 of phi dot square plus V of phi, V being the potential, and the pressure, which is the difference between kinetic energy minus potential energy. It's the same in classical physics, right? Kinetic plus potential for energy, and pressure is kinetic minus potential. So you define this, and you have a field which has a pressure and a density of energy. And so you can define what we call the equation of states. The equation of states is a ratio between pressure and rho. So you see that if I want a constant field, okay, if I want a constant density of energy, okay, I have to have W phi, which is -1, and rho phi dot is equal to 0. So a field which has a negative pressure, a field where the pressure is the opposite of the energy density of energy, negative pressure, give you a field which has a constant energy density. So constant energy density, of course, you have to think, what does it mean? I will ask you the question after, because you have constant energy density in an expanding space means I have more and more energy when my space expands. So do I conserve energy? This is a big question. Conservation of energy is not valid in an expanding space, or at least is more complex to define than in a Minkowski space. But I can define, you see, with my fields, all this property of an inflaton field, which is homogeneous with a constant energy density. So rho phi being constant, it's easy to show how the universe evolves if rho phi is constant, because this equation of motion, so W, there is no pressure for a matter field, so W equal to 0. Matter field has no pressure, of course. Radiation field, you know, everywhere the radiation field, the pressure is 1/3 of rho r. Okay, it's classical physics. Huh? Up to now, I just do classical physics. I do general relativities, but we call Milne interpretation, which means Newtonian interpretation of Einstein equations. So I have 1/3 for the equation of states for radiation fields. This is the Einstein equation. Okay, the second Einstein equation will give me the acceleration. Okay, as function of the equation of states. You just have to trust this equation. This is the Einstein equation of general relativity. So it gives me how my universe accelerates as function of my equation of states. So it's easy to show that if W is 0 or W is 1/3, okay, this is negative. So this is negative. So the acceleration is negative, is classical logical. When I have a field, a universe filled with matter or radiation, I have a pressure and, or at least I have an expansion which is slowed down because I have some matter field or some radiation will give me some pressure. But it's not the same, of course. A matter field is like this, so I have less pressure, so I extend more than the radiation field. So universe filled with matter in purple. Always purple, yellow, and green will be my code in all my seminar. Purple, matter, yellow, radiation, green, inflaton. Okay? So you see that my universe expand, but of course it slow down, right? They expand, but slow down because the acceleration is negative. In the case, of course, of a negative pressure, if I solve my equation of motion here with a W, which is a -1, I have, of course, a positive sign because minus and minus give me 1, okay? And I have rho divided by 3 m Planck square, which is positive. So when I solve my equation of motion, r dot divided by r is something, giving my exponential solution, and this is what I have, right? Very easy to find the solution. So if I have a field which has a constant density of energy, or its equivalent, a negative pressure, negative in sense minus rho phi for the pressure, I have naturally an expansion of states, which give me an expansion which is exponential, okay? Which is what we observe today, and which is what explains also the inflation. So it's quite easy to understand why in 10 to minus 36 seconds, the universe goes from 10 to minus 29 seconds to 1 centimeter, because of course, your expansion is exponential. So this inflaton field, of course, the question I have a lot of time is universe expand, okay, but in what? It's also a question which is logical. If I expand in what? Into what? So first answer for a physicist, the expansion is translated in a change of my scale factor. Okay, my metric, I call my metric GIG, G mu nu if you want, but GIG for the spatial metric, just the space and not the time. So I changed my metric. So I just change my metric by a scale, I multiply my metric by a scale factor R of t. And so I don't ask my question, I expand into what? I just have a metric would depend on time. So I don't have to think about I expand on what. It's just my unit of measurement would change with time. 1 meter is that, 1 meter is that, 1 meter is that. Just my definition of my 1 meter is changing because it's expanding with space, but I don't expand into what. I just extend, that's all. Second question, second answer can be infinite plus infinite is infinite. In the sense that if my universe is infinite, I expand infinitely, and infinite, I still have infinite. So I don't expand in something, I expand that whole. And the third answer, more for maybe if you have a dinner with your friend and people ask you, oh, I heard the universe expand. In what? It's a question of point of view. In the sense that if I'm here and I have my room, my bedroom, for instance, will expand, I should ask myself in what my bedroom is expanding. That's normal. But if I change my point of view and I reduce inside my bedroom, I will see exactly the same thing. The physics will be exactly the same. I will not see difference. When I say universe expand, you can suppose you are shrinking. It's exactly the same. You can be shrinking inside a black hole, for instance. Some theory tells you that. So you will see the same physics, and you will not ask you, I am shrinking into what? You shrink into your bedroom, right? You don't shrink into something else in your bedroom. So it's exactly the same answer that you expand into what or you shrink into what. It's exactly the same physics. So you don't expand into something, you expand that whole. You don't shrink into something, you shrink that whole. So is energy conserved in an expanding universe? This is also something which is not very well understood by people when I talk about the redshift effect or the redshift, because Doppler effect. When the light emitted from the CMB was yellow, we receive it red, more or less. Okay, you have a redshift, but I don't move, the Earth don't move, and this point doesn't move. Nobody is moving, right? The Earth is not moving. The point where the light has been emitted is not moving. Nobody is moving. The space is expanding. There is no motion, right? There is no motion through space. So this is a Doppler effect. It's true, but not classically due to the movement of motion of something relative to someone else. No one is moving relative to someone else. It's just that the light is redshifted due to the expansion of the universe because you expand the wavelengths. So the question you should ask, if my wavelength is expanding due to the expansion of my metric, where the energy is coming from or where the energy is going. Because I was yellow, now I'm red. So I let you think about this, is energy conserved or where the energy is going, because from yellow to red, I have lost some energy. And after I will answer at the end of the talk, the int is you have to define a frequency to define an energy. And to define a frequency, you need to define a metric for your time, right? This is general relativity, that your time also has its own metric. So it's because when you say conservation of energy, you should tell me in which metric, in which time, conformal time or cosmic time. So anyway, so we have passed this phase of expansion, very large expansion with the inflaton fields. And this inflaton field has to transfer his energy to the radiation field. This is a phase transition, right? You go from a space with a negative pressure to a space with a pressure of 1/3, which is light, okay? So for an inflaton radiation, this is what we call the primordial phase transition. So we have a field which is constant, and the field being constant, when you solve the equation of motion, it will begin to go to a phase of oscillation. It's just solving the equation of motion. This is just my equation of motion I show you. You have just an oscillation phase, which is very classical. I have a ball, my ball is falling, is bouncing on my soul. It's exactly the same equation. So it's exactly the same physical phenomena. My inflaton field is constant, is falling down, and it's beginning to oscillating, right? So it's exactly the same physics that you have here in the equation. So you have a phase of oscillation. So it's constant, then is oscillating. And during the oscillation, it will transfer its energy to the radiation field. A little subtlety is also between the particle and the condensate. So phi particles means you have a particle which decay or scattering, whatever you want, but it will transfer its energy to other particles that put it in black dots. A condensate is oscillating and it transfers its energy through the oscillation to particles. So you create quanta from the oscillation of the inflaton. But of course, the quanta you create will act on the inflaton and will destroy the condensate. So this is a phase called fragmentations. So phi is constant, phi oscillates. When it's oscillating, it's producing quanta. But as it's producing quanta, the quanta will quantify the oscillation itself because the quanta will attack the condensate and the condensate begin to be quantified and begin to become a particle. So a constant phi, oscillating phi being fragmented into a particle. So the story is quite easy. So this is what we call action or action-like particle. Sometimes you see action, for instance, just to come back. This is what we call an action-like particle. It's the same for the action. The physics is exactly the same for the inflaton. And this is action. So it's an action on the right, an action-like particle. So you see alp sometimes or action. The difference is the same. The coupling is the same. The physics is the same. The mass is the same. Everything is the same, except that this is zero temperature. Zero temperature means all the fields oscillate coherently. And it is quantum, of course, you increase the temperature from 0 to something else, the field begins to be quantified. It's exactly a Bose-Einstein condensate. Bose-Einstein condensate is exactly that. Bose-Einstein, you go from left to right, dropping the temperature. So we know it exists, a Bose-Einstein condensate. So inflaton is just a Bose-Einstein condensate, nothing more. So how you represent this transition between an inflaton to particle? So you just add a coupling between the inflaton and the particle. Okay, I call it phi is inflaton and chi my particle in red. Okay, So I just add the coupling, whatever is your coupling, but you see that my equation is a Matthew equation, which means that when I solve my equation, my term here has a cosinus inside it, which means it's an equation where the term itself is periodic. So it's a periodic equation with a term which is itself periodic. We call it an harmonic oscillation. We call it also it's a Matthew equation. So it is I forgot the name. So you enhance, in fact, the production. You have a resonance rate. You have a resonance effect when your frequency is half of the frequency of the term which is inside the periodic equation, right? Very classical. So this is the thing you see in the yo-yo, right? So if you here put a frequency which is the same frequency as the yo-yo, okay, you will see that. So this is inflaton, which is the hand of the guy. The yo-yo is my particle you produce. And you see that if my frequency here is half of the frequency of the yo-yo will begin to explode and to go up. Okay, so this is exactly what we call a parametric resonance. Okay, that's exactly the way the inflaton will transfer its energy toward the particle. So you can see the same also here with we have a spring here, right? And you have oscillating. The frequency of the oscillation here is not the same as the frequency of the spring. You don't see anything very particular. But when you tune the frequency of the oscillation at the same half of the frequency of the spring, you will see what we call a resonance, which appear, and you will create particles. So the inflaton is a base here, and the particle is the top. And you see that the thing on the top will begin to be produced, and you oscillate, and you produce a lot of particles. So this is very classical physics. Huh? As I told you, phi is a classical field. So all what we explain on the inflaton, it explains at the same time the exponential expansion of universe. It also explains the transfer of energy toward a thermal bath. Okay. So I will skip it, but you pass through a zone of resonances. Okay, you are stable, resonance. So you produce particle by bunch of resonances. Okay, and at the same time, you also destroy the condensate. So you destroy the condensate and you transfer the energy into bath. This is what is observed. So it is depending on the coupling I add between my inflaton and my field. So 10 to minus 8, 10 to minus 7, I increase my coupling from the top left to the bottom right. And you see that I produce by bunch, so bam, 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 bam. This is producing by resonances. And if I increase my coupling, you see that my particle in blue, my inflaton is in red on the top, my particle is in blue. You see my particle in blue begin to reach my inflaton and to be together with an inflaton, which means you begin to reach a kind of, is not a thermal bath because it's not thermal yet, but is similar to a thermal bath. You see my equation of state go from 0, okay, for instance, go to 1/3, okay? So 1/3 here, which is the equation of state of gas. So that's how you produce a gas. You oscillate, you produce resonances, and you produce a gas, okay? That's the phase transition from oscillation, from constant oscillation, then quantum states, okay? So this is what you can represent also. So you go from a condensate here on the left, okay, in purple, okay, to a particle here on the right, okay? You see on purple going down the condensate fields, we go to a particle, okay? You can observe it, this is simulations we made, okay, you have a lot of simulator to make it, so you just solve the equation of motion. It's quite complex because you have to solve the equation of motion in a space which expands, so you do some lattice, okay? You have this size, I compute solve my equation, this size, I solve my equation of motion, this size, I solve my equation of motion. So I need to solve my equation of motion in an expanding space. That's why it's quite complex and it required quite a lot of simulations. So, but as I told you, it's quasi-homogeneous, which means that phi is not exactly homogeneous, it's quasi-homogeneous. So you just saw the phi 0 of time, but I have a little delta phi because every field, of course, has some quantum fluctuations. So now I will take into account my quantum fluctuation. And this is thanks to the quantum fluctuation that we are here, because we are just son of quantum fluctuation. Okay, my universe expands. This is exponential I showed you before, but in fact, not exactly. Here it had expanded a little bit less, it had expanded a little bit more, so there is more density here than here, right? My density of phi is not exactly the same because I have a little delta phi which depend on my position. So my universe has not stopped expanding exactly at the same moment. When it stopped and it transfers energy to radiation here, universe was less dense than here. So you have some part of universe, we have more density of radiation at other part, and this little difference of density, 10 to minus 5, 1 part on 100,000, is the one who give rise to galaxies and us. Okay, this is a CMB. Okay, the CMB is just coming from the fact that the quantum fluctuations of the inflaton field of 10 to minus 5, which is exactly what we expected from the theory of inflation. We expected 10 to minus 5. We observe 10 to minus 5. It's perfect. So the quantum fluctuation corresponds exactly to what we need to form the galaxies. If the quantum fluctuation was larger, will appear too soon. If they were not here, we will not be here to explain that. So this is a simulation of the quantum fluctuation. This is a field oscillating. You see the oscillation? These oscillations, and you see the quantum fluctuations, little points, which begin to be formed. And at the end, when the oscillation stopped, because you have stopped oscillating, you finish with a space which is almost homogeneous, with some little difference, some part more than the other one. So this is a simulation of the solving the equation of motion in an expanding space. Okay, this is quite recent, and this is last year they did it. So it's this is just our universe after the inflation and during the phase of oscillations in a what we call co-moving frame, because you have to expand, of course, the cube at the same time. But here we have fixed the cube. It's what we call co-moving space to see what's happening in the oscillation. Okay, so and it's fitting quite well, and this is what you observed. Of course, you can tell me how you can create matter from nothing. So even if I don't couple my inflaton field to the matter, I still produce particles because it's related with the conservation of energy. Because in fact, geometry is energy, okay? Einstein tell you that geometry on the right, on the left, mu nu is T mu nu, which means geometry is energy. Schrödinger, people doesn't know it, it's Schrödinger in 1918, 1 year after Einstein, who put the cosmological constant on the right, okay? And who consider the cosmological constant as a field of matter. At the beginning, Einstein considered cosmological constant as a geometrical object. And Schrödinger decided to put it on the right to observe it as not a geometrical object, but as a source of energy with a constant density. Okay, T is density of energy, lambda is constant. We will cover what we said before. Constant energy density means exponential expansion of universe. So you can create, so in physics, okay, it corresponds to Unruh effect when you accelerate it in space, Schwarzschild curvature for the black hole, for instance, De Sitter curvatures for Hawking-Gibbons temperature, the Schwinger effect in electromagnetism. If I have electromagnetic fields, I accelerate it, I will create some particles, electron and positron. It's still not observed, but it is supposed. So which means the number of particles, electron and positron in the case of Schwinger effects with electromagnetism, or a particle in the case of black hole radiation, the number of particles, underline number of particles, depend on the acceleration of a deformed metric. Okay, this is very important. The number of quanta depend on your motion, okay? I don't talk about energy now. I don't talk about redshift. I talk about number of quanta, which means if I move, there is if I have a photon, I see a photon in front of me. If I move, there is a referential where the photon disappear. Not the energy decrease to zero. No. The photon disappear, okay? There is no particle. The number of particles is defined by your frame, reference frame, okay? That's very important. That Parker found in the 70s. Of course, the most famous effect is a black hole, is a Hawking radiation for the black hole, and the Schwinger effect of electromagnetism. So the number of particles depend on your frame, space frame. So if I accelerate, I produce particle. So general relativity in nutshell, very easy to understand. I have a geometric part, J mu nu, which is T mu nu, which in the geometry is energy. Let's put the way. And my energy is just 1/2 of m chi square for a scalar field, for instance. So if I have a geometry, I produce a fluctuation of chi square and vice versa. So if I have an inflaton field which accelerates, I will produce a quanta field. It's equivalence, okay? This means it's equivalence. Einstein's general relativity tell you it's equivalent to have a geometrical, which in the curvatures is equivalent to quantum fluctuations. If I have a curvature, I have a quantum fluctuation. If I have a quantum fluctuation, I have me, the sun and the photon, okay? So particles are produced from quantum fluctuation are produced from the curvature of space-time. Curvature of space-time produce particle. You accelerate, you curve the space-time, you produce particle. Okay, that the other thing is doing, okay? So it's the same for if you want, for instance, for black hole. In the black hole, when you see a metric, you have two horizons. You have the horizon of Schwarzschild horizon, RS, and you have a De Sitter horizon, which is lambda accelerating. So these two horizons, so it is correspond to potential 1/r or r square. So this is my metric I have, so dt square minus dr square. So I have two horizons, okay, which is the Schwarzschild horizon and the De Sitter horizon. Horizon means this part of space-time where the light cannot reach me, okay? So these two horizons produce your particle because they correspond to accelerations. Okay, we call it Bogoliubov transformation. So Bogoliubov transformation, in fact, is the fact that if you want to understand, I have a frequency, the omega here, okay, and my frequency in a space-time which is expanding will change. It's as if you run on the airport on this, I don't know how they call it, le tapis roulant. I would say in French, I don't know in English. A tapis roulant in the airport, right? So if you are against the tapis roulant and your speed is above the one of tapis roulant, you go to positive frequency. But if I accelerate my tapis roulant, okay, my frequency will begin to be negative because I will go fast, but slower than my tapis roulant. So my frequency go from positive to negative, which translates into a particle, from a particle to antiparticle, right? Positive frequency, negative frequency. So in a space-time which is expanding exponentially, every particle after a time will begin to be negative because my expansion is exponential. So you produce particle from the fact that your expansion is exponential. Okay. When you accelerate your expansion, you produce particle exactly the same way you are on a tapis roulant and accelerate, I begin to recede. Okay. Particle, antiparticle. That's exactly Hawking radiation. That's Hawking Gibbons operators. So H is Hubble rates, acceleration, A dot over R, let's say. So if I have a Hubble rates, I have a temperature, right? Particles mean temperature. So that's very easy. So this is what I told you. The number of particles is observer dependence. So that's quite old, huh? That's quite old because in fact, this even Schrödinger in his paper, in fact, noticed the alarming phenomena of an accelerated expansion. He tried in his own Schrödinger equation to include an expansion of space-time, and you observe that you will create a lot of antiparticle, and we should have be full of antiparticle. And he was against, in fact, an accelerating expansion because he was saying if you accelerate the universe, you should be completely full of antiparticles, which annihilate with particles and should disappear. Okay, so it is very an old question. So this is how you can produce particles from the curvature of space-time. So now we can go a little bit further. Okay, 10 to minus 10 seconds. And around this time, in fact, around, let's say, electroweak scale, this is where the dark matter become to decouple from the matter field. So you have a bath, you have produced anything with your expansion, you have produced quark, photon, gluon, and dark matter. They're all living together in a nice thermal bath. But the dark matter, because of the expansion, always because of the expansion, the dark matter we use to annihilate and produce photon, dark matter annihilate, produce photon, photon annihilate, produce dark matter. Due to the expansion, the annihilation will be weaker and weaker because the cross-section, in fact, will begin to be smaller than my expansion rate, which means that the time that two particles begin to reach together is larger than the time the universe expands. Okay, so which we call frozen out. Okay, we call it to be froze out is when the particle is out of the thermal bath. So this happened more or less for 100 TeV particle at 10 to minus 16 seconds, 100 GeV particle in 10 to minus 10 seconds, 1 GeV 10 to minus 6. And neutrino is kind of a WIMP also. It's not massive, but very small mass. Is also 1 second for the decoupling of neutrino. So dark matter is decoupled. So this is what we show for different cross sections. So you have here the density of dark matter on the left, and it will decrease because it will go out of the bath, and then it will be frozen out here. And depending on the cross section, your density depends on the value of your cross section. So depending on the cross section, you know how many dark matter is left. Okay, that's a review you can reach. And 10 to minus 10 seconds is also corresponding to the energy of the LHC. So which means more or less what LHC is testing now correspond more or less to 10 to minus 10 seconds after the Big Bang. So this kind of particle, even the dark matter will try to create on LHC or supersymmetry, why not? So this particle, in fact, should be created on appearing or decoupling of the thermal bath around 10 to minus 10 seconds. This is what we can test in accelerators. Now, of course, another possibilities. How long left? Okay, okay, still what, 20 minutes? Okay, good. So the other possibility is to produce a black hole. Because in fact, black hole can be produced also in the early universe. We call it primordial black hole because they are primordial, produced during the primordial universe. They are produced because in the story I told you, you can imagine that some part of universe was hyper overdense. Over a critical density, we call it beta C, right? And if this is a distribution of overdensity, so I can have overdensity over a critical overdensity, which is around 1. If delta rho over rho is more than over 1, you create a black hole. This is calculable. You can compute it. And so the fraction beta is the fraction of black hole compared to the total energy of the universe. And so you can create black hole, which means that I have here an overdensity. I have here my horizon. When my horizon will reach the size of my overdensity, blooms, it will collapse into a black hole. So I have some overdensity space. My overdensity will collapse into a black hole as soon as my horizon will reach it. I reach my overdensity, bloom, black hole. I reach my overdensity, bloom, black hole. So of course, if my overdensity has a size which is larger, I will collapse with a larger black hole. So I will form black hole larger and larger with time. Okay, this is what we call primordial black hole formation. So no black hole, my horizon grows to the size of one perturbation, one black hole, larger than one, a second black hole. So I form black hole larger and larger with time. So a lot of people work on this field of primordial black hole, especially since the discovery of gravitational waves, of course. Black hole has a temperature, black hole has a lifetime. Just to give you an idea, a 1 gram black hole gives you 10 to 13 GeV for the temperature, which is around the scale of the unification. So black hole can have different kind of mass, but of course, the smaller one decay very fast. Okay, the lifetime of the black hole. For instance, a black hole formed at 10 to minus 38 seconds is 1 gram. A black hole formed at 10 to minus 23 seconds is 10 to 16 gram. And you can form a solar black hole at 10 to minus 6 seconds, more or less. So before the decoupling of neutrino, this is the size of the horizon here, which is correspond to the mass of the sun. Okay, so you can form a lot of different black hole, and maybe why not supermassive black hole in the early universe. So just to give you the lifetime of a black hole is 10 to 17 seconds. Why 10 to 17? Because it's the age of universe. So for a black hole of 10 to 15 grams, so 15 grams is asteroid. So an asteroid-like black hole has a lifetime of the universe, so can be dark matter candidates, okay, because he lived at least the life of universe. So 10 to 15 gram, okay? So you got, I made this here a little story of different mass of black hole. So 1 gram is a butterfly, so it decay after 10 to minus 28 seconds. The Eiffel Tower black hole, which is more or less 10 to the 9 gram, decay after 1 second. 10 to 15 gram, I told you, it's the age of universe. Solar mass is 10 to 63 years black hole. The galaxy mass, for instance, typical Sagittarius is 10 to 79 seconds, and 10 to 115 years, 10 to 79 years, sorry, and 10 to 115 years for a black hole of the mass of the universe, visible universe. Okay, so this is typical mass, and this is the limit we have recently. This is the last limit of last year, excluded, so I don't tell you all what is the experiment. This is the density of black hole compared to the density of dark matter on the axis, depending on the mass of the black hole in solar mass. So you see that all is excluded. A little region here on the left maybe is left as a dark matter, but I will say that black hole, primordial black hole as a dark matter is mainly excluded. So the experiments are all completely different. You have nanograv here, you have some measurement of CMB, you have keV, because black hole radiates keV temperature. So you have a lot of way to discover black holes. So it can be gravitational waves, it can be gravitational lensing, it can be a radiation of the Hawking temperature. So you have a lot of way to detect it, or acting on the CMB, of course. A lot of way you have to detect black hole more or less exclude the possibility of black hole as a dark matter. Now for the present universe, will be shorter. So from 380,000 years of CMB to, let's say, the first galaxies. So the light escaped from the primordial plasma, okay, the different density we show, which has been transformed from the inflaton of the oscillation of the inflaton. And they travel toward us. It will take 13.8 billion years to reach us. And how we know from the CMB, how we know the composition of universe from this nice photo, which reach us now. I mean, this is what we see nowadays from the light which has escaped. It's exactly like a fingerprint, which is unique in each person. So it's like archaeology. From the skeleton of the dinosaur, you have to reconstruct the dinosaur. We do the same with the CMB, and we have the composition of universe from this light, which has traveled from 380,000 years to us. So that's the CMB data, so delta T over T. So this is the difference of temperature as function of the angle. So difference of temperature between here and here, here and here, and here. This is just the angle here. Okay, so you see the difference of temperature. And how we know? It's a plasma, so exactly how we know they make some experiments. The content of a fluid, the composition of a fluid, depending on the size of the waves. Okay, so this is all water. This is a mix between all water and sand. Showing, in fact, you can reconstruct the composition of the fluid from the size and the wavelengths of the waves. Okay, so you can do exam for the CMB. And this is what we see. So this is a CMB. Okay, why it is a CMB? If I take one, this is a sum of waves. In fact, I don't see it, but it's a sum of waves. If I take, for instance, this is if I take 9 red points, the reddish point here, I take 9 red points, and I make a mean of all the temperature around it. This is what I observed. This is exactly this photo here. It's just the sum of the 9 more red points, and you have make the mean of them. Which means each point you see, it's a center of a wave. So you don't see like this, it seems like blurry, but this is a sum of waves. Okay, it's a sum of waves, which is exactly a nice proof that it is a plasma from primordial universe. And you see that depending on the size of the wave, this is a lambda called dark matter. And on the bottom left, if I don't have the dark energy, you see the wave has nothing to do. On top right, no dark matter, you see nothing to do. Dark matter, dark energy, baryon, photon, to fit exactly the wave which is observed by the cosmological microwave backgrounds. That's why we know that universe is made by 27% of dark matter, 5% of bionic matter, and 70% of dark energy. So this corresponds exactly what is observed also today by the expansion of universe, but it's very nice is how you, from the CMB, you can know the content of universe just because it's a fluid, and the wave in a fluid, we call it acoustic wave. The acoustic wave in a fluid, in fact, because exactly like acoustic sound, tell you the composition of the universe. So we know the composition of the universe from the CMB. It's even more interesting is when we put some numbers because the cold point is 2.72548 degrees and the red is 2.72549 degrees. So 10 to minus and the black, and this is where we are from. So now we have the CMB, you can begin to simulate the universe to see what's happening from the CMB to now. So it's quite easy. We don't do a lot of things. We just put some more matter when it is cold and less matter when it is hot, because when it is cold, you have a gravitational potential which will keep particles together or stay together. Then the particle will, of course, gather by gravity and by pressure. Pressure and gravity will put particles together. They will form sun. The sun will form galaxies. And then normally the story is that we should observe the galaxies from the CMB. That's exactly what you do. You take the photo of the CMB and you put some simulation. You put Newton, Einstein, and Planck, curvature, gravitation, plus quantum effects. And you obtain the simulation you will see, which is illustrious, which is not the new one. I will show you a new one. This one was already 8 years ago. So you begin by, you begin by the photo of the CMB, which is the experimental data of the CMB. Okay, and you let running the simulation during 5 to 8 years. So depending, you have a lot of computers in the world who do that. So you have around 20 teams in the world who do this kind of simulations. The best one is in Durham or in Germany nowadays. And so you just let run the equation from the CMB to nowadays and to see if you can observe more or less what you observe. So you see that you will begin by universe, which is a CMB, and you see some blue part is a dark matter, of course. We know the composition from the waves. So which accumulate around point, which is colder point. And you see around that you have some, so on the bottom left, you have the years after the Big Bang. So now it's 2 billion years after the Big Bang, which correspond more or less, I mean, the Milky Way appeared 500 million years after the Big Bang, little bit after, and you see little by little the gas. So it's a simulation. Huh? So you see little by little the gas accumulating around the gravitational source of dark matter. And then they begin to have some reactions, and the gas begin to react together and to form galaxies with structures around gases, which is galaxy. So clearly you see that they gather around point with more density. So here we have 5 billion years after the Big Bang, which correspond, I mean, the Earth appeared 8 billion years after the Big Bang. So our sun is not yet there. And so you have the cube. You on the left, you see the dark matter. On the right, you see the gas. Clearly, you see dark matter does not evolve anymore. It's cold. doesn't move a lot. But of course, the gas still evolves. You still produce particles. You still produce, sorry, sun. You still produce stars and galaxies. Here we are 8 billion years after the Big Bang. So this is when the Milky Way appeared. And then little by little, you will see the gas itself will begin to stabilize because you form less and less star and less galaxies. So you see on the right, you have less and less reactions, and it's more or less stabilized, which is the universe we see today. So 10 billion years after the Big Bang. And then if the simulation is good, normally we should recover our universe from that. Okay, so the idea we ask for to artificial intelligence, to neural network, to find our galaxy. You have a simulations, and we know the size of the galaxy, we know the number of star galaxy, we know the spin of a galaxy, we know everything about galaxy. So we said to the computer, try to find an object there which seems like our galaxy and is looking. And this is what they do. So they look. So this is the size. We begin to zoom on one part of the universe, trying to find a galaxy which is similar to the Milky Way. So after a zoom, you try to find. And you can see that finding a galaxy is not so complicated. And from that, after we simulate where the dark matter should be in the galaxy from this simulation, which means that make a mean of galaxies which is similar to our galaxies, and we should look at dark matter. So this is his findings. This is a simulation. This is not a vue d'artiste. Huh? This is a real simulation after 5 years, and you recognize exactly our Milky Way, exactly the same number of stars, the same mass, the same spin, and the same size. Okay, so we find exactly the Milky Way. So, which means that all the simulations, and this is the latest one, which is 1/5 of the universe, okay, 1/5 of the universe, almost all the universe is simulated from the CMB to now. You simulate it during 13.8 billion years, and you recover exactly the universe which is observed today, exactly in the sense that you take some photos, okay, of the universe from Hubble Space Telescope or James Webb Telescope, and you find the same object in your simulation. Okay. So this is a photo, this is simulation. So you find point, in fact, with the same characteristic, and you see that in the sky is obtained by the simulations. So I don't say that we are, it's true, but we are not far from the truth. Continuous dark matter is the same. So dark matter, you know, is also observed from the CMB because of the waves, is also observed from the rotation curve of galaxy. This is what we should see, this is what we see. We see a rotation which is much, much, much larger than what we expect from a Keplerian rotation. So this is what we expect, and this is what we see. Adding the dark matter components corresponding to the 80% given by the wave of CMB, you fit exactly what you need to correspond to the rotation curve. Still corroborate. Recently, last year, I think, yes, to see, in fact, the decrease in rotation curves coming from a Keplerian decrease, maybe of the Milky Way. So maybe we begin to see the end of the dark matter halo. It is a decrease of the rotation after a size. So maybe we begin to see the end of the dark matter halo, but still in discussion. Of course, there is a bullet cluster, which has been observed, which is very nice also picture of the dark matter. Bullet cluster is 2 clusters of galaxy, which is more or less at some 1 gigaparsec from Earth, colliding, and you clearly see the gas in the center, and the matter is in blue from gravitational lensing, the gas from X-ray. So you clearly see in the photo here, the matter here, which you don't see, of course, because of the gravitational lensing, and the gas in the middle. Dark matter does not collide, so 2 dark matter pass through one to the other one. We know because the velocities, of course, is measuring, is going this direction. And of course, the gas between themselves begin to interact like this. The hair of the clusters of galaxy has been, and they are discussing together, and the dark matter continues away like a bullet inside the one without noticing that they were crossing each other. So, I mean, all this proof of dark matter, I think, is quite clear, but the nature is not yet discovered. So now we enter a new phase of inflation. So 5 minutes left. Yes, 8 minutes, still 8 minutes. Yes, you resist before the conclusion? Okay. We arrive more or less at the end. We have the phase inflation. So again, the same story. What I told you about inflation, you take the same equations, you take exactly the same things. So I can repeat it. With this field, we don't call it inflaton, we call it quintessence field. While quintessence, because from the, of course, all the fifth elements of the celestial body in Greece, was they consider there was earth, water, air, and fire. So you have to add lambda, negative pressure. Of course, we know now that we have just two elements, matter and gas. And you have to have a third element, I will say, which is the cosmological pressure. So it's exactly the same as in inflaton field. You add it on the equation of Einstein the same way. Is it a field? Is it just a constant? We don't know. The value has nothing to do. Huh? The one of the value, if I want to see difference, the value of the energy of the inflation is 10 to 12 GeV, and the value of the cosmological constant is 10 to minus 47 GeV. Okay, 10 to the 12, 10 to minus 47. So you have something like a 60 order of magnitude between the energy of the inflation and the energy you measure nowadays of the expansion rate of universe. This is given by the waves of the CMB. This is given by the recession of stars. So all agree on this negative pressure. So, a positive pressure means if I have a pump, my will push my pump down. And of course, if I have a negative pressure, it's quite a strange fluid because it's a fluid where when I push it up, it will push me up more and more the more I push it up. Okay, even if it is closed, which means I create space. Every time I create space, I create particles. Rho phi is constant, right? If I have a constant density, every time I have new space, I fill my space with my energy, right? Quintessence field means I fill my space with my energy. So, and which means I expand more, and more. So it's exactly the same story that in inflaton, but this is observed. So of course, it's observed in a lot of data. I mean, this is WMAP or Planck data, baryonic acoustic oscillation. This is, I forgot this one, yeah, supernova remnants, so expansion of supernovas. This is the pressure, rock energy density, okay? So you see more or less 67%, and -1 is W, and pressure -1. So you fit all these, -1 for supernova, CMB, here the dark energy survey. So you combine everything, you always have -1 for the equation of states, okay, with density. So you have tens of experiments, and you have a pressure which is negative. Okay, we don't know except what I told you. It's quite natural in a sense. It's a field with negative pressure, constant density. But what it is, the nature of the dark energy, we still really don't know it. So is energy conserved? This is the question I was asking. I expand my universe. I now again expand my universe. I'm beginning again, fast mention, story back. I tell my story again. Like this, the story is going back at the beginning of my talk. It seems the way. So as I say, you have to define a frequency, and it's defined, in fact, by the conformal time. In fact, if my time if my metric of my time is adapted with my metric of expansion, my red still stay red. Okay, my frequency, we see a redshift because the frequency second we have here is fixed on the fact that we have fixed my second compared to the motion of the Earth around the sun. Okay, it's defined like this, or it's defined by of course, the cesium atomic clock, but we define locally a time, right? Our time is not adapted to my expansion rate. Normally, if I have to use a real clock, I should use the conformal time, not the cosmic time, and I should change my time measurements, take into account my universe expanding because my time is also slowing down. So red still stay red. So I conserve energy. But I believe that yellow go to red because my time on Earth is not adapted to my expansion rate of universe. So now I can finish on the five last minutes on the future universe very quickly. So what will happen? We can, for instance, let's say 2043, I imagine you detect dark matter of 5 TeV. So how you detect dark matter? Particle incoming, and you see a hint of the particle on the detector. You have LZ, which gives the last results 2 months ago. So less 1 month ago. So this is the limit you have here. So we don't see anything. All this is of dark matter. So all these region here on the top is excluded. Okay, you have this little region here in white, which is the load. I suppose in 2023, why not? It has been observed by experiments LZ. They should be able to find this parameter space, dark matter eating nucleon exchanging a Higgs, for instance. Then we can go further, and we can go to maybe, why not imagine, I was discussing 2063 resonance cavity to detect gravitational waves. because when I discuss about the particle you produce, there is also graviton. And the graviton, in fact, pass from the Big Bang to now, passing through the CMB, reaching us, like the photon of the CMB. And you can detect the graviton from the Big Bang using resonance cavity, because graviton is, of course, a metric. You have a metric, I have a wave on my metric. The wave on my metric is a graviton. I have a flat metric plus a wave. And my wave, of course, is acting on G mu nu, F mu nu, F mu nu for the photon. So my graviton is interacting with my photon through the metric, of course. A photon interacts with graviton. That's why the light is bent with the sun. Okay, graviton deforms the space-time. And so the graviton can be seen by interaction of high frequency resonant cavity. This is in a lot of labs in the world. There is at least 15 or 20 experiments doing that. At Grenoble, they do it in Grenoble, at CERN, at DESY also. I mean, it's a big way of research nowadays, the resonant cavity. So you need to be around gigahertz. If I have 10 to 12 or 13 GeV in Big Bang energy correspond after the redshift, you can compute it, gigahertz. So the energy of the Big Bang at the time of the Big Bang now correspond to 1 gigahertz after the redshift. And 1 gigahertz is in the range of things which is possible to see in the resonant cavity. That's why you have so many resonant cavity papers or experimental now, because it corresponds, gigahertz corresponds to the energy of the Big Bang nowadays. And to finish, we can, so can be graviton Bremsstrahlung or anything. So in 5 billion years, the sun, of course, explodes. So we disappeared. And then in more or less between 6 and 8 billion years, Andromeda hit us. Okay, we're right to the end. So this is a simulation. We continue the simulation I show you after nowadays. And so you see that the Milky Way will be absorbed by Andromeda in more or less 6 billion years. So you have here the Milky Way, you have the Triangulum galaxy not so far, which is quite small, yes, here. And here you have Andromeda. Andromeda is a little bit larger than us, like a factor 8 more sun. And so in 8 billion years, so this is simulation, so this is exactly what will happen. The new galaxy has a name, it has a Wikipedia page, is Milkomeda, Milky Way Andromeda. So you go to Milkomeda in Wikipedia, you see, we know the mass of the galaxy, we know the number of stars, we know the spin of the galaxy Milkomeda, we know when it has been formed. I mean, everybody is so easy to know. So you have the two black holes of the two galaxies which collide together, and we form the last galaxies. And this is Milkomeda. Okay, after 6 billion years, this is what we see. This is simulation of Milkomeda. I just add this little photo here, which is quite nice on the bottom to see. So they just put the place of the Earth, okay, coordinate of Earth. And it's what you should see in the sky in 6 billion years. But don't forget, in 6 billion years, the sun will be red giant. So it will be around 3,000 degrees on Earth, so quite hot. But this is what you should see from the Earth. The Earth should not touch the suns. And so observed by gravitational waves, of course, but I think you know the story of the gravitational waves, which is the possibility to see these things. Other, and just a bit of finishing, this made observed last year is a fusion of this supermassive black hole of two galaxies. Maybe have been observed by what we call PTA, which is pulsar timing away. You have a pulsar, completely crazy when you think about that. 68 pulsar, and like a spider web. Okay, if you have a wave on the spider toile, I forgot web. Okay, you see the wave passing on the web. This is exactly what they do. They do a web of pulsar, and if a wave is passing, you see the wave from the fact the pulsar is moving. The pulsar is super precise; it's millisecond pulsar, so you can see the wave inside the galaxy, which is just incredible. A wave just deforming our galaxy. And they seem to have seen it still in discussion. It was last year, so still big discussion, but no wave in green, a wave in purple, and the dot is the data. So 68 millisecond pulsar, this is the PTA nanograph. Okay, they do it. So this is in 10 to, because it's 10 to minus 9 hertz. 1 hertz is black hole. 10 to minus 9 hertz is colliding supermassive black hole. Okay, of course, they are larger, so frequency is smaller. And 1 gigahertz is a Big Bang. So if you want to see waves, deforming waves, 1 gigahertz is deformation from the Big Bang, 1 hertz deformation from black hole colliding, and 10 to minus 9 Hertz is colliding supermassive black hole. So they conclude that maybe they have seen supermassive black hole colliding. It's stochastic, which means that they have seen a lot of waves. Exactly the same as CMB. This is waves around a galaxy, stochastic waves, huh? Which means you have waves like this in our galaxy, which means you have a lot of supermassive black hole which has been colliding during 13.8 billion light years, and our galaxy is full of waves of super black hole colliding. So still in discussion is 1 year ago so only. And so it's finished, bam. Oh, Story of Universe was long in 1 hour, right? Wow, but 1 hour for all the stories. And central black hole evaporate after 10 to 100 years, sorry. Central black hole evaporate after 10 to 102 years. Our black hole, which is a mix between Milkomeda, Andromeda, and Sagittarius. And so we finish, and the story is back again with the universe in expansion, with a field which oscillating after, and maybe we produce particle, and maybe we come back, and maybe in 10 to 500 years, people like us will discuss about the inflation, but they will take the dark energy as the inflaton in their case, not the inflaton, and they will tell the same story, who knows. So I didn't discuss about this part here. I discussed the light has not reached us. Maybe here the apple fall up. Maybe you have still some bacteria here. Maybe you have still a Big Bang here. Maybe here you have some people more clever than us, surely. So I don't know, but you can always imagine we call multiverse. Okay, I have discussed about this part here of universe. That's why it seems flat. Our universe seems flat, probably because we are just in little part. 13.8 billion years is nothing in a huge universe. That's why we believe we're in a flat universe, but you can simulate it. This is one of my colleagues who makes simulations. This is where we are, and you can simulate the expansion rate of universe in different parts of universe. We are just here, and this visible universe is just a little part here. You are here, right? And this is other part of universe that you cannot reach, but you can simulate the part of multiverse. And this is expansion rate, which means here you have a large expansion rate still. So no galaxies, of course, because the universe is still in Big Bang phase. Some parts, some valley here, where you can have life and galaxies, because of course, to have life, you need to have in a universe where expansion is not so fast to have time to form stars. So it's possible, we call it multiverse. Of course, no idea how to reach this part of the universe. Maybe white hole, maybe put there, I don't know, wormholes. Who knows? Like a log scale of the size of universe from minus 300 to nowadays. At Eratosthenes, it was more or less 10 to 4 kilometers, the size of the Earth. Then Galilei reached the size of the solar system. Then Edwin Hubble showed the distance between Andromeda and Milky Way, showed that it was a galaxy. So we go from we go to around megaparsec, which means more around 1,000 light years, 100,000 light years, even more, 1 million light years to be precise. Penzias Wilson, with the discovery of the CMB, it was more or less 13.8 billion light years. So I don't know who find it, which technology, okay, because it was, of course, the light, and of course, maybe using gravitational waves, because gravitational waves, I told you, these 6 seconds. I don't know. There will be a technology for will give me exactly the same map, but from somewhere else. I will see. So 2076. Normally, I should have reached. I just make the log scale, okay? And I reached 10 to 39 kilometers. So I know what it means. But normally, human should be able to see this other part of universe if I just follow the log scale of human discoveries. So I can skip the fine-tuning constants. For me, just a part of the universe is big. So conclusion, are we son of curvatures? Was my question. Probably yes, I say, because all what I told you was coming only from that, okay? All what I told you from the beginning is coming from this equation, nothing more, okay? You have just a geometry, a quantum fluctuation, and a cosmological constant. That's all. That's all, nothing more. This explain all the simulation I showed you before, explain you the formation of galaxies, explain you everything you just discovered, nothing more. I just need only this. I think there is 8 letters, nothing more than 8 letters. So I will conclude maybe like in Shine. Maybe the most beautiful miracle of the universe is that a fragile being like us, okay, resulting from a teeny quantum fluctuation, 10 to the -5 of the vacuum, having evolved according to the second law of thermodynamics, is able to understand the universe from which it came. Thank you. Ooh, well.
So we have time for a couple of questions?
Yes, don't hesitate. There is no simplification.
Something like young modulus for expanding universe. And if it's possible, what will be value?
Yeah, you can introduce this kind of modulus, young modulus. In fact, it's even included in some string theory. Some string theory, you have this kind of modulus which appear. And it's true that I worked in string theory and we interpreted the modulus as inflaton field. So it's sometimes the advantage of string theory has this modulus field. And so you just take one of them, we do it nowadays. So now we are doing a paper on that. So it exists in modulus and inflaton field. In fact, inflaton is a scalar field. And honestly, you have scalar field everywhere. So having an inflaton is the thing you can imagine in the world. So you're right. And the advantage of the modulus, it is string motivated. But you're right, completely right. It's a modulus field. Point. Yeah.
Thank you. I have 3 questions, but very short questions. The time you use, which time is it? Which referential are you using? In the equation of motion.
Oh, yeah, okay. So you have many cosmic, you have a lot of possible time. The 2 main one is cosmic time and conformal time. It's easier to work in a conformal time. Conformal time means my expansion, so normally it's dt squared minus a squared dx squared. A is my expansion rate, right? So I put the same dependence on my expansion on my time, right? So I extract A. I take off my expansion rate and I work in a Minkowski space, taking off my expansion, right? And the price to do that is my time now is a conformal time, right? So the easy way to compute what you see is practical, right? Is to embed the expansion rate inside the time such that I take off my expansion rate from my metric and I can work in Minkowski metric. Completely Minkowski multiplied by a scale factor. But of course, it's conformal time. So after I have to come back to cosmic time. Cosmic time is the time nowadays, okay?
Okay, well, I need really to sit on the blackboard. The second question is about antiparticles. You said that we produce more and more anti,
Yeah.
but we know that we have matter more than antimatter. So what is the reason?
Yeah.
Yeah.
Oh, this is the matter antimatter is really yeah, it's a fantastic problem. Matter antimatter. The fact is that when you put the numbers, I told you about theory, right? Now I put a number with my lambda cosmic constant 10⁻42 GeV, right? It corresponds to 1 particle produced per centimeter cube per age of universe, right? I didn't put numbers yet. I just told you you produce antiparticle, right? So acceleration, in fact, is very small. It's dominant because universe is big. But locally, you don't see lambda, right? Nobody see lambda here, right? So if I want to measure it, my antiparticle production, I should, in my centimeter cube here, I produce 1 particle per age of universe. So I will not see it. We call it Unruh effect. So the Unruh effect is you predict you produce antiparticles and particles, both of them, in fact. But from the observation point of view, you can maybe even the black hole, the curvatures, which is even faster, I mean, stronger than that, of course, it's the Schwarzschild radius, right? Infinite. Even that, the temperature is super weak. I show you the temperature of a black hole. The temperature of a black hole is a TeV, which is very small.
Okay, thank you. But the last question rapidly. You started from an inflational classical field, and then did you quantize it? Or because then you're introducing quantum physics. And we know we cannot, of course, have any unification between quantum and gravity. So how can you do that?
Yeah, so you have inflaton and graviton. It's 2 different. So inflaton is a classical field. I can make electrodynamic in a quantum theory, right? I can use Maxwell equation in a quantum theory and treating Maxwell as a classical field. No one forbid me to do that. The main difference when you compute it, it's that your field, if it's a classical field, it's just like a constant, coupling constant. You take it off the Feynman diagrams, whatever you want to with quantum theory, you take it off. You don't have A dag A if you want, right? I don't have A dag A. I don't have multiple production, right? It's I take it off, I can compute. I go from 0 to something, passing through something which is classical. Okay, from 0 to something with something which is classical here, right? But this classical field effect, okay, because I produce quantum from a classical field, like Schwinger effect. Schwinger, you have a classical field, you produce quanta, but this quanta will interact with what you produce, and you quantified phi. So phi at the beginning is classical, and with time, little by little, it begins to be quantified. It's as if you have a Bose-Einstein particle condensate, as I say, you have quantum particles, right? Okay. I put my temperature to 0, I have a classical field. You agree? All my particles will begin to oscillate at the same frequency, right? And I just have one condensate. So you have quantum particle, my temperature go to 0, oops, I begin to have a classical fields. All my particles is unlocalized. A lot of localized particle, temperature to 0, I have an unlocalized particle, right? Delta X is infinity, right? Delta T 0, delta E 0, delta X infinity, right? I'm not localized. Heisenberg principle if you want, right? If I decrease. So this is just the temperature. So 0 temperature during inflation is a condensate. 0 temperature, right? Condensate. Then I begin to produce quanta. Temperature increase. I destroy my condensate. Okay. This is passing from classic to quantum.
Thank you. Okay.
Thank you for your presentation. Early on, you mentioned the -1 number for the inflation, which passed to the 1/3 for the light and radiation. Yeah. So, but between -1 and 1/3, there's 0. So that was mass. And did it affect something or?
Yeah, it's interesting. So it's an equation to solve, which is quite strange, I admit. When you solve the equation of motion, okay, depending, I didn't discuss about the shape of motion. I put V of phi, right? Think about my potential. I have a potential, right? If you take a quadratic potential, phi square, naive, m phi square, the easiest I can imagine. When you solve the equation of motion, the oscillation, right, go like m-3. It's a dust. m-3 means I dilute like m-3. If I dilute like m-3, it means I'm a dust. W equals 0, right? But if I have a potential which is phi to the 4, not phi square, phi to the 4, I dilute like a to -4. So 1/3, like a radiation, right? In fact, my condensate oscillates, and its behavior is like a dust, like a radiation, or like anything, but it's just the behavior of the condensate. It's still a condensate. It's not a gas of matter. And I know it's even for people in our fields, a lot of time it's confusing because they take as an inflaton field, inflaton particle. It's not a particle, it's a condensate. But when my condensate, in fact, dilute with time, bouncing, going down, right? It go down like m-3, like a dust. So he has effectively an equation of state with 0 pressure, or 1/3 pressure, or whatever pressure you need. Sometimes it's 3 divided by 5. If I take 5 to the 6, you compute it, my equation of state is 3 divided by 5. 1/2, so 1/2. So I have a pressure which is 1/2 of my rho phi. In fact, I think the real point, because people say I don't believe in inflaton, I think it's the opposite. I think to have a pressure of 0 and 1/3, which is what everybody teach in university here since Aristotle, okay? So it's particular. You can think, why not having equation of state -1? Why not having 1/2? Why not having a fluid which a pressure which is 1/2 of the rho phi? I mean, it's just because in our little world is big, but I mean, in locally here, we don't feel the dark matter. We don't feel the dark energy, of course, because it's very diluted. Universe is so large that thinking that we have only matter and radiation, on the opposite, I think is quite strange. You should say, I can have this 1/2 is not as, and the second part of your question is how you pass from 0 to 1/3. You pass to 0, okay, that's your point, -1, 1/3, 0. This kind of a we don't know what's happening really, but you have a condensate and you produce particle. The particle wants to take the condensate with him, right? So it's a mix between the condensate who doesn't want to enter in the particle in the quantum world, right? He wants to resist, but the particle you produce want to bring him to 1/3. He wants to -1. He wants to 1/3. Want to -1. But there are no equilibrium in the sense that the interaction is still smaller than the expansion rates, right? So I don't enter in the bath. If my interaction is larger than expansion rates, they will begin to form a thermal bath altogether because I don't care about expansion. My expansion is large, but my particles I produce are large also, and they try to take the bath with 1/3. The inflaton with 1/3, but inflaton want to keep with 1. So it's kind of a fight between both of them, -1, okay? And at the end, one win, because inflaton decay, so 1/3 us. We win because inflaton decay. So at the end, it's time.
And just one small comment on the simulation you showed us, because it gives the same result as we observe today. Yeah. Does this confirm that the equations used for the simulation are accurate?
Yeah. Let's say it shows that the famous wave I showed you with 70% of dark energy, 26% of dark matter is correct. Okay, this is a third proof of dark matter. I show you about the wave of CMB for dark matter. I show you about the rotation curves, but few people discuss about the structure formation. We call it structure formation. That's what we call it, which means that it's very complex. Structure formation is a field which is super complex because it's non-linear equations. So to form structures in expanding is super complex. But it was not obvious that with this amount of dark matter, with this amount of dark energy, because dark energy it destroys the structures, right? How it's possible that this amount is so very fine-tuned that with the simulation, we observe exactly the galaxy appearing at 1 billion years after the Big Bang, which is what we need. So this is a third proof, okay, that we have made of. And the fourth proof, you see sometimes here BAO, bionic acoustic oscillation. That's what we call BAO experiments, BAO. It is that when you look on the sky, and this is even more impressive, when you look on the sky now, okay, not the CMB, the sky, and you make galaxy, cluster of galaxy, and you try to find the waves, you find also the same waves, which means that the galaxy in the sky follow exactly the same pattern than the CMB, with the same waves. So which means we are really in a wave. I mean, when you see and they put you exactly what I did, the waves of the space, you see we are in the middle of waves. Our universe is just a big waves. And our galaxy just follows the waves, which is also a proof that all what we do, I mean, I don't say is correct, but we are not far from the truth, let's say.
Thank you.
Vas-y.
Juste dans la liste historique, je voulais juste mentionner, si ça vous intéresse, vous pourrez vous en dire plus. Al-Falrani, au 9e siècle, avait déterminé une taille qui était de 120 millions de kilomètres. Donc, je pense qu'il était au-dessus d'Ératosthène.
Ah oui, au 9e siècle.
Oui, c'est en fait un astronome qui avait beaucoup influencé l'œuvre de Dante aussi.
Envoyez-moi un mail si vous pouvez, ce serait sympa.
Oui, avec
si vous avez le temps. Et promis,
je
rajoute.
Ok.
Très bien, ça m'intéresse beaucoup. Je vais voir si ça respecte la loi de log. Entre moins 319. Ok, peut-être. Oui, ça doit correspondre. 300, vous dites combien? 120 000? Ah ouais, entre 10 puissance 0 et 10 puissance 9. Ouais, ça correspond à ça. Ok, très bien, parfait, c'est encore mieux.
Parfait, on peut remercier encore une fois.
Et il y a une nouvelle physique pour les curieux qu'on a sorti chez Albin Michel. Je crois que j'ai fait une nouvelle physique où j'explique un peu tout ça aussi. Voilà, je pense que voilà, c'est pour des gens qui aiment la science un peu, parce que je parle du graviton aussi et de tout ce que vous avez vu là. C'est à Sagavo, pour ceux qui sont curieux, parce que je fais aussi l'histoire des sciences, le 13 janvier, sur les révolutions de Galilée à Marie Curie. Voilà, donc ce que j'écris aussi pour l'histoire des sciences. Et voilà. En tout cas, merci bien pour tout.